My name is Dr.Jarudej Asingsamanunt. I'm from the Department of Environmental Engineering, Faculty of Engineering, Kasetsart University. So my background is environmental engineering, and I did my research in the topic of hydrolysis process. So the talk today, I might not go deep into detail, but I will try to step us all back a little bit and see the biochar as the whole system in the framework of life cycle analysis. And I must admit that, like all the speakers before me, they are the top biochar experts with years of experience. So this gives me a little bit of excitement. So I will try to make the presentation as entertaining as I can. So we learned a lot from this morning how biochar can incorporate into MBS. And if we see in the bigger picture, we need to understand the concept of life cycle thinking. So everything, every product, everything that we use, including the crop, the planet, is extracted from the surface of Earth, and is go through several processes and use and in consumer use, and everything at the end is become waste. And how that waste is managed at the end is will return to the Earth's surface or below the surface or even the air somehow. And the concept of life cycle is to consider every step, the whole life. In other words, we use the term the cradle to grave. So like since it's come out of the world and it's come back to the earth. We deep into more detail into the carbon cycle. So everything that is biodegradable at the end is will return to the surface of the earth or return in terms of carbon dioxide to the air. And in this process, all the crop, the agricultural residue, or the tree killing, if we don't do anything, at some point it will fall down, rotten, and turn into CO2 or methane. Or in agricultural areas, they get open burn. So the idea here is, as a human, we amend the process by trap some of this biogenic carbon into the form of biochar, and I will talk a little more about the biochar production process in the next slide. But overall here, instead of all the carbon here, when it brought or it biodegrades into carbon dioxide or methane, some part of that carbon can be trapped in the form of biochar, its carbon here. So in terms of the nature-based solution, applying biochar into soil is the most directed idea. So we have heard about this a lot this morning, and another application of biochar is for non-soil application. Is either mixing with cement or in building material or permeable pavement or in any absorption or filtration system. But in my talk, I will move focus a little bit backward to here, because in order to make this whole process as a nature-based solution, we need to have enough understanding about the biochar production, because this system is require energy, is require heat, it still emits something to the environment. So if we don't have enough understanding about the process and the processing production of the biochar, instead of this whole thing become a NPS. If the system is mismanaged, it can become nature enemy instead of nature based. So let's talk a little bit about the biochar production process. So the term of thermochemical conversion, mainly there are two processes, pyrolysis and gasification. So generally speaking, they're both the process of heating up the biomass or the material in an absence of oxygen for pyrolysis, and in a little bit of oxygen in gasification. Let's start with the pyrolysis. Once we heat something in the chamber without oxygen, the complex molecule of the material just start breaking down. Like we cut the complex molecular chain in terms of chemical into the smaller molecule. The very small one is gas, like methane, carbon monoxide, carbon dioxide. The medium side, like the carbon atom from 6 to 10 to 20, is in liquid phase. It's either present in hydrocarbon or organic acid, like phenol or acetic acid. And the most important one that we're talking today is biochar. So any carbon that left in solid form will concentrate and compact in the molecular layer and form into char, or in this case is biochar. And let's move to gasification. It's similar to pyrolysis, but the system just apply a little bit of oxygen to make some part of the reactor become combustion, but not fully combust everything. So instead of we got the liquid product, we got just gas product with a lot of heating value, and whatever left is the black carbon-rich material, which sometimes also referred as a biochar as well. So this is technically or theory description of these two processes. So I add some fancy, nice diagram to show that in terms of gasification in the reactor, we apply a little bit, not a little bit, not too much oxygen to make sure that everything is gasified, like biomass is turned to syngas, and any solid that left is either ash or biochar. And in pyrolysis, this diagram is slightly misleading because in terms of pyrolysis, to make the system have no oxygen, most of the time there will be two layers of the reactor. Inside is pyrolysis reactor, and another layer is the combustion chamber to supply the heat to the reaction chamber. And this is the process that we get from pyrolysis. And here, this we heard about the artisanal scale biochar thing, which is up here, and this is more like a community scale or commercial or industrial scale biochar production. And I separate them into two types: is reach direct heat and indirect heat. So let's start with the direct heat. The direct heat biochar production is the clean that has just one chamber. So the chamber can be either closed or closed chamber or open. But in this chamber, the combustion zone to supply heat and pyrolysis zone are in the same vessel without any separation. But for indirect heat, like here or here, the combustion zone and the pyrolysis reactor chamber are separated by either by the wall or the bridge or the aluminum steel. And this here, we call it the contact thing. This is the one that will be steam this afternoon. So these two, in this here, the direct heat clean is the most convenient to operate, and it's the one that used widely in the rural area or in the decentralized system. And down here, this is more like an industrial scale, but it's a little bit complex to operate, but have a potential to produce high quality biochar. So here, just a little bit briefly about the mechanism, the heating step in concrete. It looks just like a cone clean, but when we look into more detail, there are some kind of air dynamic and heat supply in that. So when we light up the thing, the top layer of the biomass is combust, and when is a combustion here, the heat over here will draw the air from the edge of the flame, creating the air warming. And the fire over here will consume all oxygen. So the layer below here, there is no oxygen in front of here. So it becomes the pyrolysis area. So the material underneath the top layer will turn into the biochar. And compared to the cleaning that is use the technique of indirect heat. So up in here, in the middle of the cleaning, is the combustion chamber from here up to here, and outside around the combustion chamber is the zone of the pyrolysis reaction, and the combustion chamber and the pyrolysis chamber are separated by like a steel or stainless steel wall. So in this case, compared to the quantity in here, so the biomass just combine itself and supply the heat to the pyrolysis zone to produce biochar. But compared to here, we need to add some wood or biomass or LPG or any external fuel to supply the heat to the pyrolysis chamber. So this is the main difference between the indirect heat and the direct heat. Now we done with the processing part. Now let's briefly talk again about the biochar. So like anyone has already mentioned, like what is biochar? So it's black solid carbon rich material that produced from pyrolysis or gasification with a lot of potential to be used in either soil or non-soil application. And one thing is to trap the carbon from biomass, part of the carbon from biomass. If we use directly and put into the soil, this can act as a carbon sequestration. And this is the example of the feedstock to produce biochar. As Dr. Jarudej mentioned, the feed to produce the biochar should be come from a residue, something that we consider a waste. So, in general speaking, we do not just go out, cut the tree, and produce a biochar. And here are briefly all the potential application or potential use. If we produce in the right way and apply the right way, this can be the benefit that biochar can provide to the soil or to the environment. And this will be the summary of biochar, the summary of the application in biochar as an NBS. So this one is like one of the most important slides. So we're done. We can go for our lunch. Just kidding. So there are some great overlapping area of the biochar and charcoal and activated carbon. They all look the same. They are black solids, granulate or powder. And I just would like to express their difference so that when we talk about either when we talk about biochar or charcoal, we are in the same place. So the first thing, let's see at the feedstock. As I just said, biochar, the thing that will become biochar is residue or the waste. So something that have no option left to be used. But in some cases, for charcoal, people just walk into the forest, cut down trees, and bring it to produce the charcoal. And the charcoal is used mainly for as a fuel, either for cooking or for providing the heat. But at the end, when the biomass is turned to charcoal, it will get burned. So all the carbon in that biomass at the end, it will release to the air compared to the biochar. When we see the black carbon powder as a biochar, we see it as a material, not as a fuel. As a material, we will use it either in soil or as a filter or as a fuel material in construction material or something else. And the costs are similar, and the production in biochar production, I would say that is the operator or the thought of the production in biochar. We tend to add more sustainable way compared to the charcoal that they can just burn it in the soil cleaning like this and release a lot of smoke to the environment compared to the biochar production that we put more care into the air pollution control of the syngas from the system. This is the comparison between charcoal and biochar. If we talk about activated carbon is another level. Is the much higher grade in terms of the material, and the production process is much more complicated. And when we talk about activated carbon, it's more like we will use it as in absorption or as a environmental polluting control. We don't care about we care less about the production process because the production process involves high ingredient or chemical activation, which will contribute to a lot of carbon footprint compared to just the biochar. And we heard a lot of talk from our speaker in the morning. It's like for biochar, if we produce it in the right way or with proper processing or upgradation, is also work in terms of environmental pollutant control compared to activated carbon. So it's like it might not as good as activated carbon, but it can go up close to that level, which more cost efficient and sustainable way to produce. And here is just the sample of the artisanal scale that is easy to break. And something like this, we will use in this afternoon to produce the biochar. And just repeat what Professor Benedict just mentioned. The open burning with excess or sufficient oxygen supply will create the orange red flame compared to the open burning with limit oxygen supply, so it's create a lot of heat. What this picture means is that sometimes open burning is not a bad guy. If the open burning has enough oxygen supply, it produces a lot of heat, and heat is the product that have a variety of use. But just happen in like in Thailand or any other developing country, when we talk about open burning, the situation is like more like a picture on the right than the left. So the incomplete, when I say incomplete, it means limit oxygen supply. The incomplete open burning, it will create a lot of smoke, and this smoke is like a volatile organic compound, CO2, methane, carbon monoxide. This is sort of the air pressure, the sort of PM 2.5. So the real bad guy is the smoke here. So when we operate the quantity clean, we harness this technique. So it's some kind similar to open burning, but we open burn in the right way to use the oxygen supply from the side of the flame. And the flame here will act as a flame curtain. So the flame will act as a shield or barrier to oxidize or combust any gas here that might occur from inside of the heat. So here is briefly a little bit about what we will do this afternoon. So we will have a quantity clean like this. We load in the wood or our feedstock. We start lighting the flames. So once the thing is right, the flame go up, we keep apply or load the wood biomass into the kiln in the constant level to sustain the flame into this. So around 1 or 2 hours once the kiln is almost full, we quench it with water, so we get a biochar like this. And the level of the rate when we add the biomass into the kiln is not too low or too high, but just enough to sustain the shape of the flame like this. So the flame can maintain its shape and maintain itself to oxidize or any gas that occurs from inside of the flame to up here. And so I just recycle the picture here. So like and how you create the vortex. So hopefully I will operate the clip right and you see this picture in the afternoon and the people around in the building will shock what are we doing, we see a lot of fire. Now we get it to the point. So we understand the overview of the process. We understand we use the biomass that is a waste or residue. So now let's move to the concept of LCA. If you see here, the life cycle assessment, they use the same pattern with the life cycle thinking. So we consider the material, we consider something once it extracts from the earth surface until it's turned back to the earth. We consider all the steps just to understand how it impacts the environment. So we normalize it into one unit. In most cases, it's CO2 emission, but there are other units as well, like land use, biodiversity. But the most general way is normalizing and integrating in terms of CO2. And the first step of LCA is to define the scope. For example, in our case, in biochar production, so the scope is like when we got the biomass, and the biomass is fed into the kiln, to the process, and we got the product. And after that is the application use of the product. So during the process, we just combust or convert the biomass into biochar. So in terms of effluent or waste, there are very little or negligible. Only effluent here is might be the water that we use to quench the biochar, but that water can be reused. So in the case of we reuse the water, there will be no effluent at risk here. The only concern is about emission, because the system requires us to combust something to provide heat. When we say combust here, it's because of the pyrolysis or the gasification of the biomass to produce a biochar. Overall is endothermic reaction. So it means we need to add some energy. In this form is we burn the top layer to add some heat to the layer below so that the biomass can release the syngas. We look in more detail for the scope and definition. We can separate it into 4 blocks. Like we got a feedstock, right? We may need to characterize. We need to understand what type of feedstock, like wheat straw, corn cob, or Kasetsart, because they all have different carbon content, different fiber structure, like cellulose, lignin, and all that will contribute to the production. Like what clean we use. In our case, in example, we use quantity, but in some places they may use the retort clean or different type of clean. This all contribute to different LCA impact from the system. And once we got the biochar, it also depends on the process parameter that we set and the type of the biomass. Or the carbon that originally in the feedstock, how much carbon that concentrate in the biochar, and how much other elements like oxygen, nitrogen that are still left in the biochar. This will identify the application. First, just easier is the inventory analysis. So it's like the activity, the things that occur throughout the entire chain of the biochar. Each one of these, in the detailed calculation for LCA, each one of these will have their emission factor, like a converting unit to convert that activity into the level of emission of CO2. For example, the very basic one is like the transportation. Like the transportation of biomass from where it left to the clean. The type of the car, the type of the engine will have a specific number per kilometer to calculate in terms of the emission. And it was suggested by, I think by CSI, that the distance should be below 50 kilometers from where biomass occurs to the clean. And here, this is the complicated one because in the production, there are a lot of parameters to control in the pyrolysis process. The first one is temperature. Like the higher temperature we want to go, the more energy we need to input. That means the more CO2 we need to clean in terms of energy, like fuel consumption. And now in the biochar, the most important one is carbon content. How much carbon that we trap, how much original carbon from feedstock that we trap biochar. It's like if we produce the biochar with very low yield and with very low carbon content, it means that we lost a lot of carbon in terms of the gas or the liquid product. And after that, the use of biochar is like how we ensure that the carbon that we trap here will stay in the solid form for more than like 100 or few hundred years. And this is the database from TGO, and some data from here is not available in national or the LCA database. Some of them we need to derive ourselves, or we need to find the literature research. And here, roughly, is the result from the wood chip biomass converting to biochar using the quantity clean. So to get one biochar, the emission is 1.77 kilograms CO2. And if we compare to the full combustion, the wet combustion of the biomass, this will be around 2 to 3 kilograms. So the biochar production produces less amount of CO2. And if we see in the detail, like the transportation of the wood, the material required to produce the clean, and the everything, most important one is burning of the wood. This means that almost like 70 to 90% or more than 90% of the CO2 contribution in biochar LCA is coming from energy requirement to make the pyrolysis happen. So in here, overall is 1.77. So like the CO2 from burning the wood to supply system is more than 90%. But this is only the case for continuous cleaning. Imagine if the clean over here is not continuous, is the industrial scale with a lot of reaction chamber and screw and pump and a lot of mechanical parts to make the process continuous and a lot of mechanical moving parts. This means the material for the city cells will require more stainless steel, more material. So the footprint from here can be higher. But the overall, the hotspot for the emission from LCA in biochar mostly is come from the energy requirement, either from burning the wood by itself or using the LPG or the electricity. And to make the picture more clear, if we imagine this is the one chunk of the wood biomass, in the wood biomass there will be a water content, volatile matter, fixed carbon, and ash content. This proportion is from the bamboo biochar. The left one is the full combustion. When we fully combust something, we only have an ash left. So all the carbon or all the thing in here will turn into gas, which means that 90% of the carbon here turn into carbon dioxide. But compared to pyrolysis, either with the quantity clean or any pyrolysis process, when we pyrolyze something, most of the volatile matter will turn into gas or liquid oil, liquid product. But the fixed carbon and some carbon in volatile matter are still stayed in the form of biochar and ash. So this difference from here to here is at least equal to 30% or some cases more than 50 of CO2 reduction compared to the baseline, and the baseline here is full combustion, direct combustion, which reflects the application, the utilization of biomass, like in electricity and for fully combustion. If we compare this with the open burning or we left over to make it rot into methane, the reduction here will be much bigger. And here, roughly in terms of roughly general number, when we say how much carbon we can save from producing 1 kilogram of biochar, let's say roughly at the minimum point is almost 1 kilogram of CO2 saving per 1 biochar production. The best case can be more than 2.5 or even 3, depending on the baseline that we compare. And just for more information, 1 kilogram of carbon dioxide is equal to 500 liters. So it's like the water bottle that we have, the CO2 in that bottle for 100 bottles, that equal to 1 kilogram. So to generate 1 carbon credit is to save 1 ton of CO2, and that 1 ton of CO2, considering this volume, 1 ton of CO2 will equal to like a 2-story single house. And just to translate this unit mass of CO2 in terms of the volume that we can understand easily. And here, this is a concept that reflects the life cycle thinking and the carbon cycle. So like if we do nothing, the biomass will just rot or convert or biodegrade. So the carbon from the biomass will fully return as a CO2. But if we produce the biochar and apply it to the soil or use it in the right way, up to 50% of the carbon in here can be trapped into the soil. So this is the way that we incorporate the biochar as a measurement solution and also become supporting to help the country achieve zero emission. And here, just translate like everything that from the baseline, either direct biomechanical or direct combustion compared to the biochar production, the pyrolysis. So there will be some cut off, like the trade-off that produce the lower amount of the CO2. So this is the source of the carbon credit, which is also the potential benefit of the biochar as well. But I will try not to focus too much on carbon credit because we're talking about biochar as the ADS solution here. So this is we may heard more of this in the picture. And this is the overall, I try to simplify all the work that I just present. So like we have a lot of pile of biomass and production, we have any type of cleaning, and the biochar that we got will reflect from the type of biomass and the process condition. And the property will also reflect the application. This is the four main building blocks of the biochar system. And this will be my ongoing research that I collaborated with everyone to understand more detail of this. Like the number that I just presented is just the number from quantity clean. So roughly when we say about the example of LCA in biochar or any place, any application, it tends to be very generic information. So if we want to understand the site-specific data, we need to know what exactly the biomass they use, what type of the clean, the retort, the quantity, or the big one, the continuous, what material, a lot of detail, and what condition in their operation. So all this data, if we link all together, we can specifically derive the emission factor to use to update the LCA to calculate more specific situation for each biochar production, as well as understanding the, I would say, like feedstock process product relationship, so that we can customize what type of biochar we want for a certain application that we want to use. And here, after we do the biochar production, we have like a extra topic. So in this case, we will have we will apply a biochar into some in my conceptual design for as a water filtration, like to reduce the suspended solid or water turbidity. So a little bit more detail in chemistry. We have heard a lot of potential in biochar. So in biochar, not just the porosity on the surface area that they have, the functional unit like the carbon oxygen bond, carbon hydrogen bond, they all create different characteristics, and each characteristic will have different reactions towards some certain contaminant. The first block here is the mechanism that occurs when the biochar is used to absorb the ions, like heavy metal or metal ion. The one in the middle is the mechanism of biochar absorbing organic contaminant, like nitrate, phosphates, or pesticides, something like that. And this one is when biochar interacts with microbes or by bacteria or even pathogens. So I'm not going to go in detail for everyone that happened here, but the important thing is like to understand the type of biomass and the process condition to customize for each one of these. If we have a target pollutant that we want to absorb, we can identify which one we want to have and link back to the process condition to maximize. For example, if we want our biochar to have a lot of, let's say, surface of the patient and electrostatic attraction with maybe heavy metal, we can link back to the process parameter to make sure that the biochar have this functionality so that it can maximize the absorption. And this is also maybe not just biochar, the biochar can be upgraded, can integrate or add some, like we can coat the biochar with some certain material to make it more suitable for filtration or absorption. This is the theory, the detailed theory when we apply the biochar as the filter media or absorption. And from here, because the biochar has a lot of function, which can identify using the FTIR. And this is the newest tool that I just have my bachelor final year project student to create this. The machine is called, technically it's called polyometer. So it's the machine to measure the water contact angle. And this is the DIY version, like using the smartphone to capture the shape of the droplet and the contact angle of the droplet to the biochar. And this contact angle will also reflect the FTIR fingerprints, like how it interacts with water. Is it hydrophobia or hydrophilic? And to separate the biochar from hydrophilic or hydrophobia, we also reflect the application either in soil or absorb some pollutants. So this is the ongoing research, and I'm open for any collaboration. And here, this will be the experiment that we will see in late afternoon production. So I have some small filtering column filled with gravel, fine sand, and charcoal for slow filtration. So in theory, the gravel will screen any big particle out of the water. And if the sand is left for filtration long enough, there will be a biofilm to help purify water or trap any small particle. And the charcoal, in this case, is a biochar, to help screen or absorb smaller particle, either a sustainless solid or a nitrate or potassium molecule from the water. Or in some cases, it can absorb the dissolved solid or solid from the water. But the process is very fundamental. Somehow it cannot totally purify the water, but it just helps the water get cleaner. Which this content is very suitable for rural area where clean water is very hard to access. And applying the biochar here is more like a cost efficient and more sustainable compared to activated carbon. This will be the things that we will experience this afternoon. And this is the end. So,
it was such an excellent talk. The thing is that explained very clearly. Is there any question? Everybody will be happy for lunch now. And so, no more any question? Yes,
according to you, yes, what is the key compartment CO2 emissions when we're producing biochar?
So, in the context of artisanal cleaning, the first thing is the biomass need to be dry enough. Let's say like the water content need to be less than 20%. And when we combust the biomass into the clean, it should be the correct particle size, like not too small or not too big. And the rate of inputting not to be too much, so that like the top layer of the biomass will get burned slowly. It still emit a CO2, but just right amount of CO2 should apply the heat to the system without any other VOC. And to answer the question directly, it's like the way we cannot reduce it to zero. Somehow there will be some CO2 anyway. The only way that we make sure that we release the CO2 just to the extent that we provide enough heat to make the reaction happen. And that can be done by if I say very general that it can be done at experience, the operator experience, because it's artisanal thing, we don't have a sensor or the complex to measure the pressure or anything. So it requires the experience from the operator to see the shape of the flame, to see when the clean starts smoldering. This maybe we add too much biomass or the biomass all the way to the ash already. So the way of inputting is very important. This is the context of artisanal. But when we think about the industrial scale, that is depend on how continuous the process. It's like how the system maintain the heat transfer and the input. Like when the previous kick start, you may need to use the LPG to raise the temperature. But once the biomass is released the syngas, if the system can recycle the syngas and maintain the energy, that is fine, because that is minimize extra fuel. So that is the point that where the CO2 emission is lowest. But that's the ideal scenario. We don't need any extra fuel supply.
Thank you.
Okay. So if no further questions,
Maybe like I would like you to clarify, since I want to build on what she asked. Like you said that when you are inputting the biomass, the size should be not too be small or not too large.
Yeah.
So I would like to ask, knowing like specific size.
Okay, so the specific size will relate to the size of the clean as well. There will be in terms of quantity. If the size is like less than 2 meters in diameter, the input biomass, right? The wood size it will be like less than the length of the biomass should be less than your hand, something like that. This is based on my experience. And if the clean is big, there will be a clean that's like 2.5 meters diameter for a bamboo. So like the length of the bamboo can be like this long, like my arm. Yeah. But in most of the continuous clean, it's different story. The input biomass, the particle size need to be much smaller because when the process is continuous, the feed need to be flowable. So it needs to be small in terms of particle size, and it's just flow together. So it's going to be like this size, but it's like less than a fist. Yeah.
Excuse me, as you mentioned that biochar can capture the metal, right? Yes, I would like to know what's the next process after it's capture the metal and what we do next.
That will be one more like entire research area. It's either in the metal or any pollutant when the biochar is spent to extract some pollutant, either heavy metal or pesticide or any pollutant. There must be some kind of regeneration process so that biochar can be used. Otherwise, like the very common thing right now include with activated carbon after they are spent. If they are beyond regeneration, they get fully lost, like they are incinerated. But if that case happens with biochar, so all the attempt to trap the carbon, to save the carbon with biochar will be gone. So in that scenario, we can consider only we use the biochar as a biomass-based utilization to mitigate the environmental pollution via absorption. Just that we don't have benefit from carbon reduction. But in the ideal scenario, if that biochar can be regenerated, either by using the catalyst or we heat or we hydrolyze again and we use that biochar to use, that will be two benefits, like reducing the carbon by trapping the carbon into block biochar, and that biochar can be keep using for absorption of the material. But that is ideal scenario. If we can do that, I think we reached already. And at some point, the biochar need to disposed because the capacity to absorb should be decreased over and over every cycle.
If I may add, if we have the biochar that absorb the heavy metal, maybe we put it in the concrete or something like that, because it will stay there like a long time. It may be one of the solutions. That.
No more question. Okay.